I've been recently on the Flat Earth Discord server and I was asked how the radius of the Earth was measured. I answered by looking at the night sky. My answer was welcomed with laughters, insults, and derogatory memes. Someone asked me to explain how looking at the sky could help measure the ground, and proposed an analogy with a table and a light bulb, saying that looking at the light bulb cannot help you figure out what shape is the table. As I was explaining that, yes, it does, I realized that it was quite difficult to explain just with words, so I decided to make a short video. So here is our table. It is flat, and if we move around the table, we can see that for any object in our field of vision, we can measure the angle between the object and the horizon. Let's imagine that our observer is moving towards a street lamp situated on the table, and measure the angle between the street lamp and the horizon. Let's try to plot the angle with the distance covered. On the horizontal axis, I will put the distance covered, and on the vertical axis, the angle between the street lamp and the horizon. At 0-degree angle, it is the horizon in front of the observer. So I represent it with the tablecloth. If the street lamp is far away in front of the observer, it will appear close to the horizon, and therefore the angle will be small. When the street lamp is straight over the observer's head, it will make a 90-degree angle with the horizon. And when the street lamp is far away behind the observer, it will again appear close to the horizon, and the angle will be close to 180 degrees, which is the horizon behind the observer that I represented with the tablecloth. Let's now plot the angle with the distance on our graph. As you can see, the angle barely changes when the street lamp is far and changes rapidly when the observer passes under it. It is interesting to note that as long as the table is large enough, the shape of this plot will be the same whatever the distance between the street lamp and the table. Even if the street lamp is thousands of kilometers away, there will be a point where one will be right under it, and the rate of change will be high. And if one can go as far away from the street lamp as one wishes, there will be points where it will appear close to the horizon, and the rate of angle change will be negligible. Let's go back to our table. Do you see that screen on the wall in front of the observer? It is on the other side of the room, quite far away. And as you can see, as we move towards it, the angle between the horizon and the screen doesn't change. Now, if instead, when we move around the table, we see this. First, you might agree that this is already a strong indication that the table might be curved, or at least it certainly gives that impression. Let's now imagine that our observer is moving on a curved surface and measures the angle between the horizon and the screen. Notice, first, that the angles seem to change with a constant rate with the distance covered. Notice also that the screen will appear to go under the horizon and even straight down under the table from the observer's perspective, something that one does not expect to see on a flat table. Let's now plot the angle with the distance covered on the graph from before. As expected, this is a straight line. Here we see the screen set, the moment where the screen goes under the horizon. And here we see the screen rise, the moment where the screen appears on the horizon. And as one covers the entirety of the circumference, the angle goes from 0 to 360 degrees. And you might have guessed it, you now just need to measure the distance traveled to go around. The circumference of a circle is 2 pi r. You divide both sides by 2 pi and you get the radius of the curvature. So this might be doable on a table, but for something as big as the Earth, this might not be practical. But the good news is, we don't need to travel an arc length that covers an entire circle. Any arc length is described by the same equation, and therefore any arc length traveled could allow us to derive the radius of the Earth, as long as the angle measured, b minus a, is greater than the instrument's minimum resolvable angle, But of course, the longer the distance traveled, the more precise the measurement. If we go back to our table then, and measure the distance that we traveled, we could use this distance traveled as the arc length, and therefore obtain the radius of the table. What you just saw happening with the objects in this room is precisely what happens with the stars in the night sky if we travel north or south on the Earth. Don't take my word for it, test it for yourself. I even gave an idea of an experiment that can be done to test it. I don't know which map you use, so I've searched for the flat Earth map and this is the one I found. Assuming that you agree that different places along the same meridian experience the same time, meaning when it is midday somewhere along the meridian, it is midday everywhere along the meridian. Which means that, except for polar regions, when it is nighttime somewhere along the meridian, it is nighttime everywhere along the meridian. The test would consist in having different people at different latitudes along the same meridian, possibly at regular intervals, and asking them to point a camera to the south or to the north and take a picture the same night at the same time. The image sequence thus obtained would result in something similar to what I've shown in this video. Astronomers have known this for thousands of years, and this is what motivated them to hypothesize that the Earth wasn't flat. Okay, so this is how it is possible to measure the curvature of a table by looking at a light bulb or screen. But it's important to say, did I presuppose that the table was curved to make my measurement? Yes, I did. I also presuppose that all of the angle change is attributable to the curvature of the table, and not because the object is close, for example. I justify this presupposition by observing that the objects in the room all rotate with the same rate. They don't have different relative angle change. Their angles don't change relative to one another, unlike the angle of the computer screen and the clouds in the first example. Is the observation that the room rotates as we travel around the table enough to conclusively assert that the table isn't flat? No, it is not. But the proponents of the flat table need to contend with the fact that the sky behaves that way,